Hello everyone, this is the part 5th of the important formulas and concepts for GATE 2023. So first we will see this Avrami relationship. So in this Avrami kinetics, the rate of transformation is given by the Avrami equation with the fraction of transformed related to the time. So this transform fraction is given by f, and the formula is f is equal to 1 minus e to the power minus c t to the power n. So we can write 1 minus f equal to e to the power minus c t to the power n. So where c and n are the constant for a particular temperature, we can directly put the fraction transformed into this equation and we can calculate the constant c and n, and if this t is given. Now we will see the interfacial energy relationships. So in this, assuming that the second phase is nucleating at the grain boundaries, and the interfacial surface energies of the matrix precipitate boundary and the grain boundary energy of the matrix, that is gamma GB, and this is matrix precipitate boundary, so gamma MP. And this is fixed at a dihedral angle theta between the matrix precipitate interface. So the formula will be gamma matrix and grain boundary is equal to 2 gamma matrix precipitate. This is the surface energy for the matrix precipitate. This is the surface energy of the matrix and grain boundary. So gamma is equal to 2 gamma cos theta by 2. So gamma GB is equal to, the formula will be like gamma of GB is equal to gamma of matrix precipitate surface energy 2 gamma matrix precipitate surface energy cos of theta by 2. So directly we can put the values and we can get the answer. So this gamma mgb is the interfacial surface energy of the matrix precipitate boundary, and gamma mp is the grain boundary energy of the matrix and precipitate. So dihedral angle theta between the matrix precipitate interface. The degree of polymerization, it is defined as the average length of a linear polymer is represented by the degree of polymerization or the number of repeat units in the chain. The degree of polymerization can also be defined as a degree of polymerization is equal to average molecular weight of polymer and divide by molecular weight of the repeating unit. So if we will divide this average molecular weight of the polymer divide by molecular weight of repeating unit, so that will give the degree of polymerization. About critical fiber length, a critical fiber length LC for any given fiber diameter D can be determined according to this formula. LC is equal to capital T multiplied by SF and multiplied by D divided by 2 of tau T. So this is the formula where TSF is the tensile strength of the fiber, that is capital T and capital, this is the tensile strength of the fiber, and this tau I is related to the strength of the bond between fiber and the matrix, or the stress at which the matrix begins to deform. Now we will see this drift velocity. So this is the average velocity between the collision of two electrons. So it is defined as sigma E is equal to nqv. So this is the drift velocity. Electric power P is equal to Vi is equal to I square R. This is the formula. And conductivity of semiconductor, that is sigma is equal to N multiplied by Q multiplied by mu plus P Q mu, where sigma is the electrical conductivity, E is the electrical field, and N is the number of charge carriers, and Q is the charge on each carrier, and V is the voltage, I is the current, and R is the resistance. Mu N and mu P, mu N and mu P. So these are the mobilities of electrons and holes. Mu N for electrons and mu P for holes. Yes, this is also here. N and P represent the concentration of the free electrons and holes in the semiconductor. This Nernst equation, so the electrode potential depends on the concentration of the electrolyte. At 25 degrees centigrade, the Nernst equation gives the electrode potential in non-standard solutions. So the equation is E is equal to E naught plus 0.0592 divided by N log of C ion. This is the C ion of the metal in a molar units. This is also mentioned here. And E is the electrode potential in a solution containing a concentration. N is the charge on the metallic ion, and E naught is the standard electrode potential in 1 molar solution. About Faraday's equation, the amount of metal plated on the cathode in electroplating or removed from the anode by corrosion can be determined from Faraday's equation. The Faraday equation will be this: W is equal to I dot T dot M divided by NF, where W is the weight of plated or corroded, that is in gram, I is the current, that is in ampere, M is the atomic mass of the metal, N is the charge on the metallic ion, T is the time, that is in seconds, and F is the Faraday constant. Its value is this one. Pilling-Bedworth ratio. So this ratio we generally do it in case of corrosion. So Pilling-Bedworth ratio is defined as the oxide volume per metal ion divided by metal volume per metal atom. Actually this is atom. Yeah, both are atom. Oxide volume per metal atom divided by metal volume per metal atom. If this ratio, this Pilling-Bedworth ratio is less than 1, if this ratio is less than 1, then what happened? The oxide occupies a smaller volume than the metal from which it is formed. The coating is therefore porous and oxidation continues rapidly and typical of metals such as magnesium. So if it is less than 1, then oxidation will be very fast. If the ratio is 1 to 2, that is the range. If this ratio is between 1 to 2, then what happened? The volume of the oxide and metal are similar and adherent. So non-porous protective film forms, typical of aluminium and titanium. Basically, we generally see that the layer of aluminium, that is Al2O3, we find in general cases. So that is protective film. If the ratio exceeds more than 2, like 2 or more than 2, then the oxide occupies a large volume and may flake from the surface and exposing fresh metal that continues to oxidize, typical of iron. You see the rusting of iron. So in that case, this ratio is greater than 2. Okay, now we will see this, how to measure ductility or how to calculate ductility. So what is ductility? That can be defined by two ways, that percentage elongation, or we can say the reduction in area. So these are the two ways to define the ductility. In case of percentage elongation, you can see what is the final length and what is the initial length. So the final length minus initial length divided by initial length multiplied by 100, that will give the percentage elongation of any metal, that is called the ductility of that metal. And if we define the ductility with the help of reduction of area, so we will see the initial area minus final area divided by initial area and multiplied by 100, that will give the reduction of area. So this is also can be transformed like A naught L naught is equal to A L. So this is the volume that will be constant. So we can define like this, what is the ductility. So where LF is the final length, L naught is the initial gauge length, AF is the final cross section area, and A naught is the initial cross section area. Okay, so generally we see two kinds of stress whenever we are going to deform any metallic specimen. So first is hydrostatic stress and second is stress deviator. Stress deviator. So we see in a matrix like sigma 1 1 1 2 1 3, sigma 2 1 2 2 2 3, sigma 3 1 3 2 and 3 3. Then through this matrix we can see what are the components we need to calculate the hydrostatic stress, and rest of we need to calculate the stress deviator. So these are the principal stresses sigma 1 1 2 2 and 3 3 which are required to calculate the hydrostatic stress. So this is the formula sigma h, this is h for hydrostatic. Sigma h is equal to 1 by 3 sigma 1 1 plus 2 2 plus 3 3, and we take the mean of the all three principal stresses. This will give you the value of hydrostatic stress, and these rest of 6 components we required generally for calculating this stress deviator. Yes. Okay, now we'll see the stored dislocation energy. So the stored dislocation energy, whenever a material is plastically deformed, the energy stored in the material is this stored dislocation energy. So this is defined by the formula E is equal to GB square by 2, where E is the stored dislocation energy and G is the shear modulus and B is the Burgers vector. Now we will see the, actually this is slip systems, this is the slip systems in FCC. So in case of face centered cubic, this is the face centered cubic. So the most dense plane and dense direction makes the slip system in case of FCC. In general case also, but in case of FCC we will see the most dense plane. This is like 111, we will see in the unit cell. So this is the 111 plane. If this is the origin, then this is the 111 plane. So this is the 111 plane and direction is 1. This is the family of 110 direction. This is the family of 111 plane. So we can say the number of planes, this is 4, like 1 is this, and we can also make like one more plane 2, and we can also make like this 3 and like here. So there are 4 planes, and direction per plane this is 3, so it is multiplied 4 into 3, like gives you total 12 number of slip systems in case of FCC. Okay, so here also mistake, slip systems in case of BCC. So in BCC total we have a 48 slip systems. This is 12 plus 12, 24, and this again, so this is gives you 48. So in this case the slip planes are family of 110 plane, family of 112 plane, and family of 123 plane. The corresponding directions are 111, this is the most dense direction, but family of 111 direction is different with each plane, so it will make the combination of 6 to 12, and this 12 and 1, this is 12, and this is also makes the 24 into 1, that is 24. So it will give you total 48 slip systems. Now we will see the slip systems in case of HCP. So here slip plane count, this is the basal plane 001, and slip direction is 11 bar 20. So this is the most common slip system in case of SCP. So it contains only 3 slip systems, and others are also available, and these are the prismatic planes, and this kind of family of plane is related to the pyramidal one. So this slip system in SCP also depends on the C by A ratio. So for the exact C by A ratio 1.63 follows few metals, that is like magnesium, and whenever C by A is less than 1.63, that is, and whenever C by A is greater than 1.63, that follows Zn and cadmium, like zinc and cadmium. This is titanium and zirconium, this is magnesium. So these kind of 3 categories with the C by A ratio which define the slip system in case of SCP. So one more formula from diffusion, that is diffusion coefficient. So D is equal to D naught exponential minus Q by RT, where Q is the activation energy, R is the gas constant, T is the temperature, and D naught is the diffusion coefficient, and D is the diffusibility. So diffusibility is directly proportional to the temperature. As we increase the temperature, diffusibility will be more, and D and D naught both have the same unit, that is meter square per second. So thank you.